The rank of a matrix is a measure of how many independent rows or columns it contains. Think of it as the number of directions that the data in the matrix can point to without being redundant. If you picture each row as a recipe, the rank tells you the smallest number of recipes you need to recreate every other recipe by mixing them together. The normal form, more formally called row echelon form, is a stair-like arrangement obtained after systematic row operations. In this form, every leading first non-zero entry of a row is to the right of the leading entry of the row above it. All entries below a leading entry are zero, and any all zero rows are at the bottom. This shape makes the independent rows obvious, and therefore reveals the rank directly. 3 elementary row operations are allowed because they mimic reshuffling or scaling a set of equations without changing the underlying solution space. Swap 2 rows like swapping 2 recipes, the set of recipes stays the same. Multiply a row by a non-zero constant, like doubling every ingredient in a recipe. The direction of the recipe does not change. Add a multiple of one row to another, like adding a portion of one recipe to another. The overall space spanned by the rows does not shrink or expand. Because each operation is reversible, the number of independent rows, the rank, remains unchanged throughout the transformation to row echelon form. To bring any matrix to row echelon form, follow these tidy steps much like sorting a deck of cards. Start at the top left corner position 1-1. Find the first column that contains a non-zero entry. If the entry at the current pivot position is 0, swap with a lower row that has a non-zero entry in that column. Create a pivot by scaling the pivot row, so that the pivot becomes one optional for row echelon required for reduced row echelon. Clear below for every row below the pivot, subtract an appropriate multiple of the pivot row, so that all entries beneath the pivot become 0. Move to the next column to the right and the next row down and repeat the process. When a column has no non-zero entries below the current row, skip it and move further right. Stop when you have processed all rows or columns. The result is a staircase of leading ones or any non-zero leading entries with zeros underneath, which is the row echelon form. A useful mental picture: each step of the algorithm peels off a layer of independent information, pushing the remaining dependents further down and to the right. Once the matrix is in row echelon form, the rank is simply the count of rows that are not completely zero. Each non-zero row has a leading entry that is linearly independent of the rows above it, so each contributes 1 to the rank. Practically scan the matrix from top to bottom every time you encounter a row whose all entries are 0. Stop counting the rows below, are also 0 by definition of the echelon form. The final count is the rank, denoted rank of A. This method works because row echelon form preserves the row space, and the 0 rows represent no new direction. Consider the 2 by 3 matrix A equals start matrix with first row 2, 4, 6 and second row 1, 2, 3 end matrix. Step 1. Use row 2 as the pivot. It is already smaller. No swap needed. Step 2. Make the leading entry of row 2 a 1. It already is. Step 3. Eliminate the entry below it in row 1 column 1 by doing R1 becomes R1 minus 2 R2. R1 equals bracket 2, 4, 6 close bracket minus 2 bracket 1, 2, 3 close bracket equals bracket 0, 0, 0 close bracket. The matrix now looks like a bracket with first row 0, 0, 0 and second row 1, 2, 3 end bracket. Swap the rows to bring the non-zero row on top. A bracket with first row 1, 2, 3 and second row 0, 0, 0 end bracket. This is row echelon form. There is one non-zero row, so rank of A equals 1. The intuitive picture: the second row is just a half scale of the first, so they point in the same direction, only one independent recipe. Take a 4 by 4 matrix that contains parameters A, B, C. B equals the matrix with first row 1, 2, 3, 4, second row 2, 4, 6, 8, third row A, B, C, 1, fourth row 0, 0, 0, 0. Step 1. Row 2 is twice row 1, so replace R2 with R2 minus 2 R1, which makes row 2 become all zeros. Step 2. Use row 1 as pivot. Eliminate the entry in row 3 by replacing R3 with R3 minus a R1. Resulting row 3, A minus A times 1, B minus A times 2, C minus A times 3, 1 minus A times 4 equals 0, B minus 2 A, C minus 3 A, 1 minus 4A. Now the matrix is first row 1, 2, 3, 4, second row all zeros, third row 0, B minus 2, a C minus 3, a 1 minus 4, a fourth row all zeros. Step 3, if B minus 2 is not equal to 0, use that as the next pivot and clear below which there is nothing below. The matrix then has two non-zero rows, so rank equals 2. If B minus 2 equals 0 but C minus 3 is not 0 or 1 minus 4 is not 0, the third row still has a leading non-zero entry further to the right, giving rank 2 as well. The leading position just moves right. Only when all of B minus 2, C minus 3, and 1 minus 4 are 0 does the third row become 0, leaving only the first row non-zero, so rank equals 1. Hence, rank of B equals 2 if the triple B minus 2, C minus 3, 1 minus 4 is not the 0 triple. Equals 1 if B equals 2, C equals 3, and 1 equals 4a. The parameter conditions tell you when the third row becomes a linear combination of the first, mirroring real-world situations, where a new measurement adds no fresh information, unless the parameters satisfy certain relationships. Pitfall 1. Forgetting the zero-row rule. In exams, students sometimes count the total number of rows, ignoring that rows that become completely zero after reduction do not contribute to rank. Quick check. After you have the echelon form, simply glance for any row that is all zeros, exclude it. Pitfall 2. Mixing up row rank and column rank. The rank is the same either way, but if you stop after row operations and look at columns, you might miss dependencies. Remember, you only need to count non-zero rows, columns are automatically handled. Pitfall 3. Not using the simplest pivot. Choosing a pivot that is a large number can cause arithmetic errors. Swap to a row with the smallest non-zero entry, or a 1. When possible, this reduces computation time and the chance of mistakes. Quick check strategy. After reaching echelon form, write down the positions of the leading entries the staircase. The number of stairs equals the rank. If you are pressed for time, you can also stop early. As soon as you have identified k independent rows and the remaining rows are linear combinations of them, for example they become zeros after elimination, you already know the rank is k. Another shortcut. For a matrix of size m by n, the rank cannot exceed the minimum of m and n. If you quickly find the minimum of m and n independent rows, you can stop. The rank is maximal. These tricks help avoid common algebraic slip-ups and save valuable minutes during a timed exam. Question 1B.Tech 2019 Paper 2. Find the rank of M equals the matrix with rows 1, 2, 3, 4, 5, 6, 7, 8, 9. A solution. Step 1. Row 2 is replaced by row 2 minus 4 times row 1, giving the row 0 minus 3 minus 6. Step 2. Row 3 is replaced by row 3 minus 7 times row 1, giving the row 0 minus 6 minus 12. Step 3. Now row 3 is replaced by row 3 minus 2 times row 2, giving the row 0, 0, 0. The echelon form is the matrix with rows 1, 2, 3, 0 minus 3 minus 6, 0, 0, 0. There are two non-zero rows, therefore the rank of M is 2. Question 2. Mechanical Engineering 2021 Final. For the matrix P equals the 4 by 4 matrix with first row a 1, 0, 2. Second row 2, a 1, 0, third row 0, 2, a 1, fourth row 1, 0, 2, determine the rank in terms of the parameter A. Solution brief outline. Step 1. Perform the row operations. Replace row 2 by row 2 minus 2 times row 1, leave row 3 unchanged, and replace row 4 by row 4 minus row 1. After simplification, the matrix becomes the matrix with rows a 1, 0, 2, 0, a minus 2, 1, minus 4, 0, 2, a 1, 0, minus 1, 2, a minus 2. Step 2. Use the second row as a pivot, provided A is not equal to 2. Eliminate the 2 in row 3 and the minus 1 in row 4. After a few elementary steps, you obtain a triangular form whose diagonal entries are a minus 2, a squared minus 4, a plus 3, and a cubed minus 6, a squared plus 11, a minus 6. Step 3. The rank drops when any diagonal entry becomes 0. If A equals 2, the second diagonal entry vanishes, and further reduction shows only 2 independent rows remain, so the rank is 2. If A equals 1 or A equals 3, the third diagonal entry is squared minus 4 a plus 3, which factors as open parenthesis a minus 1 close parenthesis open parenthesis a minus 3 close parenthesis, becomes 0. But the fourth entry open parenthesis a minus 1 close parenthesis open parenthesis a minus 2 close parenthesis open parenthesis a minus 3 close parenthesis is non-zero, giving rank 3. For all other values of A, including a not equal to 1, 2, or 3, all diagonal entries are non-zero, so the rank is 4. Final answer, the rank of P equals 2 when A equals 2, equals 3 when A equals 1 or 3, and equals 4 otherwise. Both examples illustrate how the row echelon process turns a messy matrix into a clear staircase, from which the rank is read instantly.